Hi, so this is Will Thomas recording the first part of the exam. So the exam is where we are given a network of pipes where node 0 is connected to 1 and 2, and 1 is connected to 2, and 1 and 2 are connected to the outside environment. We are given some values for some of the properties of the pipes, and we are tasked with finding the height at node 0 and a value for k that gets us these flow rates. Q equals 5 times 10 to the negative 4 and 2.5 times 10 to the negative 4 for nodes 1 and 2 respectively. Supposed to use value of E over D for 0.001 for all the pipes, and tells us some good initial guesses. So if we look at what's given here, part 1 of the exam is to actually have some functions calculate the head drop and the flow rate of a single pipe segment. So let's go over to some pen and paper and figure out how we do that. So we're now at pen and paper, and now we're starting with this equation. And so the first thing we're tasked to do is given a flow rate, find the change in head. Now this is relatively simple because as we see here, head is just the pressure divided by the density of the fluid times gravity plus some height z. And here we see pressure divided by density times gravity plus a height z. So if we want to find the change in head, that's just head of 1 minus head of 2, which can be rewritten, which is what this side is, just rewritten a little bit. So head of 2 is pressure at 2 over rho g plus z2, head of 2, minus head of 1, which is, factor out this negative negative, so we have P1 over rho g plus Z1. So this side right now already is the change in head. So meaning, this is over G, by the way, sorry. Now, meaning that we just need to figure out what this side of the equation is, and that's minus 2 FLV squared over G times D. We know what 2 is, we know what G is, we know what D is, we know what L is. These two are a bit of an issue though, but easily solved, easily fixed. Now, let's start first with the V. So we're given a flow rate, but we know that the flow rate is just proportional to the velocity of the fluid itself if we divide the flow rate by the area. And if we do that, since the area of the pipe is a circle, we just divide by the area of the circle with, we have D instead of R. So in that case, it'll be 4 times Q over pi D squared. Now this is the value of V. We can sub this into V here in the coding itself. If we want, we can calculate V first and then use that value of V in the code here itself. Now, on to this value of F. F is a bit harder to find, but it's still relatively easy. We have F, and there's many ways to find F here, but the way we're going to find F in this equation is based off this thing called the Churchill equation, and that's just a way that we use Reynolds number, which is the pressure, or which is the density times the velocity times the diameter of the pipe divided by the viscosity of the fluid. And we use this, and we use the roughness of the pipe, which is epsilon over D. So what F can be rewritten as is a function of the Reynolds number and E over D. So what does that mean for us? Well, because we know the Reynolds number, which is V, which we know because it's just proportional to the flow rate, we know what the Reynolds number is, and this will be given and the E over D part will be given in terms from the problem because it is a property of the pipe. Now, because this is a nonlinear equation, and I'll show you what this actually looks like at the computer in a minute, we can now figure out what F is. And now, because we we know what this term, all the terms here are equal to. We know all the terms here. We know what G is, we know what D is, we know what L is. We now know what V is here, and we know what F is because F, we can find that based off the Churchill equation. And the Churchill equation is based off the Reynolds number, which we have here, which we know everything here. So finding the change in head based off the given flow rate is relatively simple. The issue is when we we're given the change of head but need to find the relative flow rate to that, because now F and V are both unknowns because these are both focused based on Q. What we can do here though is, because we're given this is just a number, equals 2FLV squared over GD, and because this is both unknowns, we need to solve this numerically. But we'll get into more of this after we code the first part. So here we are at the coding screen, and first things first, we need to import numpy as np. Next thing we need to do is we need to figure out a way to calculate f, because that's how that's one of the variables we need for the friction factor. So first things first, we need to figure out how we do that. We do that by using the Churchill equation. We do that with this here, where we have f is equaling this, a and b are equaling these two things that match here. So all we need as the input is the Reynolds number and the value of E over D. But just a quick note, this is a Darcy friction factor, and we need this is the incorrect version, so we need to divide this number by 4. So when we return the result of f, we only need to have a 2 out front, not a 8. So what this looks like, this is define f to be the input, where we need Reynolds number, and we need E over D. And we just need to copy this over, and I'm just going to do it off camera and cut to it because that takes way too long. So we see now here, this is just where we take E over D as the variable, and we calculate A, we calculate B, and we return 2 times this number because it's 2, not 4 or 8, because I said we divide by 4 to get from Darcy to the one we actually need. So we have this. Cool. The next thing we need to do is we need to start defining some values of the pipe that we're doing, or we're working with. So that would be the length of the pipe, and we would also need, say, the diameter of the pipe. We would also need pi. We would also need G. These are some constants that we would just need. We would need the density of the fluid we're working with, and the viscosity of the fluid we're working with, because we use this to find the value of the Reynolds number, which is here. And we would also need to find, or to have, pressure at 0.1 and the pressure at 0.2. Also need Z1 and Z2. So the problem here doesn't really specify which values to use for the single pipe segment, so I'm just going to put in some numbers. So we're going to call L to be 110 meters. We're going to be, the diameter is going to be 10 centimeters. Pi is equal to np dot pi. G is equal to 9.81. Rho is going to be, we're working with water, so this is going to be a density of 1,000. Viscosity will be the inverse of that, so that will be that. Pressure 1 will be at 0 because it'll be atmospheric, and pressure 2 we'll call that, I don't know, that many, a million. And we'll call Z1 to be equal to 0, and we'll call z2 to be equal to 10 meters, drops 10 meters. So, ooh, yeah, this is equals there. Yeah. So that's what we need. So now that we have some parameters of the equation, since we're finding the change in head, we should probably define the head as well. So head 1 is equal to P1 divided by rho plus Z1, and head 2 is equal to P2 divided by rho plus Z2. So now we have this. Now we have a bunch of variables that we can use. What fun, what great fun. So now that we have the info for our pipes and a way to calculate F, we can just start defining the function d head to be the change in head. And we can figure out what goes into it later. But at the end of it, we need to return, wow, to return -2 times F times L times V squared divided by G divided by D. So that's really nice, but how do we do that? So first things first, we need to figure out what V is. Remember, V was equal to the flow rate over the area, and in that case, that was 4 times the flow rate divided by pi divided by the diameter squared. And how do we find L? Well, if you remember that, or how do we find F? Remember that F was just the, F is up here, so instead of F we need to have FB RE ED. So now we have that. So to make this actually work, we need to figure out what the Reynolds number is. So the Reynolds number, we're defining that to be equal to, remember that's rho times the velocity and times the diameter divided by mu, which is the viscosity. So now that we have the Reynolds number, we can, so now we have a way to calculate all of this that returns our change in head. So what values actually go into d of head, and those values are Q for the flow rate, E over D for the roughness, L, and D, because those are the ones that might change. So that's how we find the function for the change in head. So now that we've figured out the first function, I want to briefly review how we do the second function. So now that we're given the change in head, these two things become a number, and it's just equal to this set of variables. And before it was easy because we only had one unknown, we could solve it like directly, but now, because we don't know the flow rate, we don't know V, or we don't know F, and we have to solve this numerically now because there's no other way to solve symbolically because now there's two unknowns. So what that means is we need to figure out when either like this number minus this equals 0 or this plus this equals 0. It really depends on how we set up the code itself, but the emphasis is that we need to solve this numerically where we relate these two things and they somehow become 0. Cool. So now we're back here coding, and so we need to define a function called this flow, and oops. And what this does is we need to have this output a flow rate based off of delta head. So we need to have one of our inputs be delta head. Delta head. Yeah, cool. Delta head. So what do we do from here? We need to have remember how we do this, we have our input delta head, and we need to subtract that from our calculated delta head that we're going to iteratively solve over and over again using numerically, in this case using Newton's method. And in that case, we need to have a function, we call this f to 0, where this f to 0 takes in all of our, subtracts our iteratively calculated change in head from our input delta head, and then we try to bring that function to 0 using Newton's method. So that looks like we can use our previously calculated d head function and then subtract that from our guess of our input of delta head. Now, so what does that mean now? So we have our delta head, and for this delta head we need to include this, all the variables that we needed before to calculate delta head, so all these d, and we need to bring this to the outside, and we also need to bring the rest of these variables to the outside too, so that they can be brought into this. And because this is what we're actually trying to bring to 0, we can just return this immediately. Cool. Nope. And from here, what do we need to do? We need to actually solve this numerically. So how do we do that? We use Newton's method. So how do we do that? We have to go up here and we do from SciPy dot optimize. We need to import Newton. Easy as that. SciPy dot optimize, import Newton. Boom, easy. Now, from here, all we need to do is have our actual numerical solve, where we have our function that we need to bring to 0, that would be f to 0. And we need some kind of guess. So in this case, we're just going to call this QGuess. And that means we need to define the QGuess up here. QGuess. And we're going to call this 1 for right now. Easy. And then after we figure out after we solve this numerically using Newton's method, we just need to return the results. So figure out that we're good. Because just to review, we've had this flow and it's delta, and it has input of the delta head and the geometry of the pipe, and then we pump that into a function that we actually need to bring to 0 because we calculate the delta head iteratively based off this Q, and our delta head, make sure we bring this to 0, and we return that result. And up until now, we've been able to directly type in Q and ED, but let's just maybe define Q and ED separately, so we don't need to do that anymore if we're just running tests for it. So 0.01 looks good. So that's how we have a function that defines that. So now that we have this function that works, this is pretty good. We just need to improve it a little bit to add a bit of functionality on the boundary conditions or some extraneous conditions that we might not have thought about the first time around. So what do those things look like? So the first thing I can think of is, if this works great, is if the flow rate is going from 2 to 1, or from 1 to 2. But if it's going from 2 to 1, the flow rate's going backwards, and based off how we have this Newton factor, this Newton solving, it breaks. So if we have flow, for example, of 2 Q E D L and D, this breaks because backwards and it doesn't really want to behave. So this can break in multiple places and we need to fix all of them. So first things first, we have the error in where if we have a negative flow rate, this means our V is negative, and that V makes our Reynolds number negative, but the Reynolds number is never really defined for anything below 0. It only produces good values for when Reynolds number is above 0. So how do we take care of that? Well, we just need to wrap this whole thing in the absolute value bar. So np.abs. And now we have a positive flow rate all of the time, meaning we have a positive Reynolds number value all of the time. But that isn't the only fix we need to do, because now this would return if we had a negative flow rate, it would return the positive flow rate anyway. So all we need to do is multiply by the sign of the flow rate, because right now here it's still negative, but we're making it positive, so we need to make it negative again here. So we just do multiply by np dot sign of q. So here this retains the same sort of sign. Next thing we need to do is down here at the delta head. This is sort of the same thing here, where if the delta head is negative, then if the delta head is positive, that means that the water is going in the reverse direction. So we need to account for that here. So we can just call this the ABS delta head. Delta head, which is equal to np.abs of delta head, which is np.abs of delta head. Cool. So now that we have ABS delta head, now we can bring this to here, so it's still positive. So now we bring ABS delta head. Let's put one of these underscores here so that differentiate it easier. So now we have the fix, so the Newton's method does not break immediately, but we just need to, once again, like we did up here, multiply by the sign of delta head in the first place. So times np dot sign of delta head. And this should work. Oop. Oop, 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 oop. And now we have a negative flow rate. So how cool is that? Because before, when we have negative, it was negative because that means the delta head's going downward towards the end of the pipe, so it's a positive flow rate. But now, if we have a positive flow rate, it doesn't break anymore. And the last thing, and another thing I want to change to this is if the flow rate is 0, it works some of the time, but not all of the time. So I want to code it in so when we save on runtime, if the delta head is 0, it just spits out 0. So if delta head equals 0, or not really 0, but if the delta head is less than or equal to one number, so we're going to say 1 times e to the negative 10, then we're just going to have it return 0, because at that point we don't need to have any extra runtime, because if it's just because if it is just 0, then we don't want the computer to run any longer than it has to, because that means it's just 0. And then at this point, I think that's part 1 done. Cool, because once we have this p0, return 0, and that's all we really need to do. Cool, thank you.